All right, guys, so I want to go through some stuff with Thermo today. Uh, you should have gotten a worksheet. You guys did so much better second time through with calorimetry. We did an awesome job. So continue to work on that. Continue to go through some of those questions. You picked up a couple of worksheets were handed out to you as you came in. What we're going to move on to is talking about using thermochemistry and Stoich. And hopefully what we're going to do today you'll find pretty easy, or at least easier than what we maybe have done so far up into this, because we're just going to apply the same concepts that we've talked about prior to this. So the first thing we want to talk about, if you look at the worksheet that you picked up, we're on the side, again, says problem bank. It says chapter review problem bank. So it's the really dark black copy. So we want to figure out endothermic, exothermic. So if we're talking again, endothermic, exothermic, if we talk about, putting something in water, if that reaction or that metal is losing energy, that means that the heat of water is going to increase. Well, that means the heat of the reaction is going to go down. And when we do this, this is what we would be calling our exothermic reaction. And then again, if we do something similar, but we do the opposite to what it was, and energy goes into the reaction or that metal, then that means the Q of our water is going to go down and the Q of the reaction is going to go up. We've talked about this. This would be our endothermic reaction. So what we want to be able to do is to look at these chemical equations and figure out, first of all, are they endothermic or exothermic? So to do that, we want to know, what do each of these things mean? So this here, these are, remember, my reactants, and then this is all my product. So if we look at this chemical equation right here, what we can glean from that and what we can infer is that this heat right here, one, is a product, and if it's a product, it's being produced. So if we're producing heat, we can make the assumption that that's exothermic, right? Because if we're producing heat, it's going to the surrounding down here, it's exothermic. So again here, we're going to find our heat. So what's that? Well, that should be exothermic as well. Now we come over on this side. Now our heat is found as a reactant. So for this reaction to happen, for iron and carbon dioxide to react to make iron oxide and carbon monoxide, I need heat to do it, which means I have to take heat from my surroundings. And when I do that, this is going to be endothermic. So same thing for this one. It's part of the reactant, so we're going to call that endothermic. So if we do that then, if we look at our next one, what you might want to write out, like on a side somewhere or on your worksheet, there's a little space on the top. Exothermic versus endothermic reactions. Well, one way to represent it is like this. The reactants yield products plus heat measured in kilojoules, and this is important. It's always going to be in kilojoules because, again, that heat really is the molar heat of reaction, which is delta H, which is going to be measured in kilojoules per mole. So we can put it in the products. If it's an endothermic reaction, then this heat here is going to be in our reactant side, and we're going to yield products. That's one way that we're going to see it. Now, if you look at number 35 on there, well, now it's not in the equation anymore. Now it's just our delta H. So we need to think about what's happening here. So when our delta H is negative, then we can make the assumption that if delta H equals the Q of the reaction divided by the number of moles, we're never going to have a negative number of moles. So if it's negative, that means that the Q of reaction has to be negative. And if the Q of reaction is negative, that means the Q of H2O is positive. And if we look back to the drawing that we did a second ago, if we look here, if the Q of the water is positive and the Q of the reaction is negative, that means it's exothermic. So in this reaction here, what's happening? Well, we have our reaction, water is positive. The reaction is negative. That's why we get that negative, which means energy is moving out, which makes this exothermic. If it's positive, the opposite is happening. That would be endothermic. Again here, positive, endothermic. Positive, endothermic. So again, same thing we just wrote before. We can put it right into the chemical equation itself. Reactants yields products plus heat. That would be an exothermic reaction. Or we can just leave the delta H. Really, this is what you're going to see more often. So again, that's telling us if this is negative, that means the heat of reaction was negative, which means the heat of water in that calorimetry problem was positive. And if we did that, that means it's exothermic. Or in opposite, endothermic, heat is one of the reactants, yields the products, or we leave it as delta H. That positive tells us that the heat of reaction was positive, which means the heat of water is going to be negative, which means we're losing energy. So another thing that we can represent it as is what we call an enthalpy diagram. Now, as enthalpy increases, if we look at this, first of all, we need to figure out, is this endothermic or exothermic? Well, it's endothermic, right? Because it's gaining energy, right? It's positive. So what we're going to do for a enthalpy diagram is we're going to write our formula of what we start with, and if it's endothermic, we're going to show that it's gaining heat. Now, for now, I'm not super concerned about getting this to the right point. But as we move up, as enthalpy increases, we're going to gain heat. It's going to go up. So if we had an exothermic reaction, similar to this one here, same thing, enthalpy is increasing as we go up, except now, that's a negative molar heat of reaction, which means this is an exothermic reaction. And if that's exothermic, we're going to start with our products, or our reactants, excuse me, up here. And then we're going to show that as the reaction happens, that they are losing energy. And as they lose energy as it goes down, this is our enthalpy diagram that we're going to draw. So if we look back to what we've had every time, these are two ways, and then the other way, with an enthalpy diagram, if it's let's erase that. Oops. So if it's exothermic, we're going to start high and go down. If we're endothermic, then we're going to have that heat increase as we're going in our enthalpy diagram. So this is like what we're going to use today. How much heat will be released if 6 grams of carbon reacts with excess oxygen according to the equation below? Now, for this one at least, I want to write out and put it into our equation. So C carbon plus oxygen gas yields carbon dioxide. And because we know it's exothermic, it's negative, that it's one of the products, and 394 kilojoules. Now, we're going to follow the same process we followed over and over and over again, which is we're going to build a roadmap. We're given grams carbon. The only thing I can convert to, again, is moles of carbon. And then we can convert straight to heat in kilojoules. So this is how we're going to do it. To draw my T-chart, I start with 6.0 grams of carbon. Let's make that decimal better. I want to get rid of grams of carbon. And again, because I'm going to follow my roadmap, I'm going to go to moles, carbon. And whenever we're going grams to moles, it's 1 mole. 1 mole of carbon is 12.01 grams. Then I want to get rid of moles of carbon. And it says I can go straight to kilojoules. So now what I'm going to use is I'm going to use my mole ratio. So in this equation, there's 1 mole, because this is my coefficient here, right? And if there's no coefficient, then we make the assumption that there is 1. And then we're going to come over here. This is now my coefficient. So I'm going to put 394 there. And then when we plug it in, we're going to plug 6 divided by 12.01 times 394. And we're going to get 196.835 kilojoules. Oh. Now, if we want to be really technical, how much heat will be released up here? Well, we could put a negative to make sure that we know that it's being released. You don't need to put that negative. You can just write 196.835 kilojoules, because when we're talking about it, if it says how much is going to be released, if I said how much money do you lose, or did you lose in the stock market? Well, you wouldn't tell me I lost negative $40,000. You'd just say I lost $40,000. Because of the phrasing, we know that it's negative if it's released. When we plug it in, we're going to plug it in there that way. So if you flip over to the other side of 12.2, this is your homework. These 10 questions and then the 4 on that worksheet that say thermochemistry plus stoichiometry. So I want to do a couple of these quick together with you. So again, first one here. We're given how much heat will be released when 6.44 grams of sulfur reacts with excess oxygen gas according to the following equation. Well, first, let's put it in, and it's exothermic because it's negative molar heat of reaction. So 2SO3 plus 791.4 kilojoules. So, roadmap, grams of sulfur to moles of sulfur to heat in kilojoules. So we're going to start with our T-chart, 6.44 grams of sulfur. I want now to get rid of sulfur, so get rid of grams at least. I'm going to go grams to moles. Again, when we go grams to moles, it's always 1. If we look on our periodic table, 32.07 grams, moles of sulfur to kilojoules, grams cancels, moles cancel. Coefficient mole ratio, 2 moles, 791.4 kilojoules. And when we multiply all of this out, we're going to go 6.44 divided by 32.07 divided by 2 times 791.4, and we end up with 79.46 kilojoules of heat is going to be released. I want to do one more, and then you're going to have some time to work on this. So again, how much heat will be absorbed now? So just from these statements, released and absorbed, we should immediately be able to figure out, is this endo or exothermic? Well, if it's absorbed, it's going to be endothermic. So now we're going to put heat as one of our reactants. So I'm going to write this out. Now, as you're doing these, you don't necessarily have to write this if you understand how this plugs in. But I'm going to write it this way because I think it's easier to see in the formula. So roadmap, grams of nitrogen. And I'm going to go from there to moles of nitrogen. And then from there, I'm going to go to heat. Just a mole ratio. So let's solve this. I'm given 13.7 grams of nitrogen. I want to get rid of grams of nitrogen and go to moles of nitrogen. Again, grams will cancel. 1 mole, because when we go from grams to moles, this is going to be 28.02. If you use your periodic table, nitrogen is 14.01. We have 2 of them. Then moles into kilojoules, 180. When we go in, 13.7 divided by 28.02 times 180, we end up getting 88 kilojoules of heat is going to be absorbed. If you have questions, let me know. If not, then you have a couple worksheets to work on, and you should have adequate time to get those knocked out before you leave today. Have a great weekend.